We're going to do a little bit of lecturing on some of the nomenclature stuff that I did with the other half of the class the other day, just to make sure everybody's on the same page. That way on Monday, we'll all come back together and finish up everything from this chapter together. Afterwards, if you do have questions on anything, I'll be more than happy to hang out and answer your questions if you have specific questions on anything else. But I did want to get into some of the nomenclature I know was what was on tap for this week for lab. So hopefully you got some of the information, but if not, let's just make sure. So let's talk a little bit about nomenclature. And nomenclature is really the naming of everything. And as we were talking about with bonding today, really there's two types of ways that we name things, and it does involve the type of bonds that occur, whether it's an ionic bond or sort of a covalent bond. And if it's ionic, as we were just talking about earlier today, that's definitely a metal and a non-metal together. And as we talked about, that's when we get that transfer of electrons. And obviously our cation, which is positively charged, and our anion, which is negatively charged. And the way we name these guys are different than how we name covalent compounds, or they're sometimes just referred to as molecular compounds as well. And that's basically our guys who are going to be sharing electrons like we were talking about today. Everybody's kind of sharing the electrons together, and that is usually between two nonmetals. And again, we have sharing of electrons that is happening here. So based on what type of compound you come across when you go to name something, there are specific rules that you have to follow based on what you are naming at that particular time. We're going to talk about, again, those rules to make sure everybody, hopefully, again, is on the same page here. So first off, though, there are certain things that, regardless of what they are or how well they are supposed to be technically named, they do kind of go by common names. And I would say probably these first three are the ones that we really come across a lot. H2O, if you see H2O, again, is not a trick question. It is water, and that is how you should name it. It is not dihydrogen monoxide, because nobody wants a refreshing glass of dihydrogen monoxide. It doesn't sound really nice and all those type of things. NH3 is ammonia, which shouldn't be confused with something else that we will see, which is ammonium. This has no charge. It's NH3 and it's ammonia. CH4 is methane. That is the simplest organic molecule you could have. And it's really what kind of comes out of the vents there when you light a Bunsen burner. It's the methane that you light on fire. NaCl, I'll be honest with you, sodium chloride is what most people will call it, but some people do refer to it as sort of table salt and then table sugar. So I would say, like I said, these three here, if you come across them, you really should use only those names: water for H2O, ammonia for NH3, and methane for CH4. Now, when we name common binary compounds, like I said, they're basically composed of two elements. And as we talked about, those are two classifications: metal and non-metal. No sharing of electrons, going to be an ionic compound, and compounds where we do share electrons, which is really going to be molecular or covalent, where we are sharing electrons equally, unequally. It doesn't matter in terms of naming, but we do name them differently. When we have just ions by themselves, which are things that are charged. So for example, if we have a cation, which are positively charged guys, like our sodium, that is +1, our lithium, there it is, +1. To name these guys, we actually just use the whole entire name of the element. So this would be the sodium ion. This would be the lithium ion. This would be the magnesium ion. So really any positive ion by itself, you pretty much just use the whole name, including for H+, this would be the hydrogen ion as well. Now, when we name negatively charged ions that are negatively charged, these guys actually get, you use the base of the name, and then you actually add IDE to the last part of the name. So I should say that a little bit better. You actually drop the last part of the name and replace it with IDE. So something like Cl- is chlorine. That then becomes the chloride IDE ion. If we have something like oxygen there, O2-, that becomes oxygen, becomes the oxide ion. Now, hydrogen is one of the only elements that could kind of go both ways. It could actually be negative as well. And we can have a negative version of hydrogen, which is known as the hydride, IDE ion. Hydrogen, for the most part, is going to be positively charged. It will only be really negatively charged if it comes after a metal. So if you have a metal and then hydrogen, that's going to be the negative version of it. But if you have basically hydrogen with other nonmetals, it will be positively charged. Any questions on that there? If you're asked to if you're asked to write the formula for the ion, it should always include charges. So if you're asked to write the individual formula for a cation or an anion, it should always have the charges written with it. But as we will talk about when we put them together, should ever have any charge. All right. So before we get too far, I don't know if we talked about it or not, but let's make sure. When we look at the periodic table, there are certain things that have fixed charges, right? Things in group 1 and group 2. Everybody in group 1 will always make a +1 charge. Everybody in group 2 will make a +2 charge. Then we got 3, 4, 5, 6, 7, 8. But transition metal is really small. In group 3, which is really aluminum, we'll always make a +3 charge. We actually skip group 4 because that's sort of like where the staircase kind of comes down through there. Group 5 will be -5. -5, no, not it will be -3. That's like nitrogen and phosphorus. Group 6 will be -2. And group 7 will be -1. These are fixed charges. They will always have that charge no matter what the situation is. For example, sodium is group 1. You will never find a sodium with anything other than a +1 charge when it does make it. When we talk about our negative guys, as we talked about today, we are talking about our nonmetals. Yeah, so we're talking about the nonmetals above the staircase. Because a reminder that if you go below the staircase where like lead, tin, and all those guys are, those are actually metals and positively charged. So we're talking about above the staircase where the non-metals are the guys that will make those negative charges. The transition metals in the middle there have a variable charge. So pretty much everybody in here and even down in here have a variable positive charge, which means, for example, something like iron in certain cases could be iron +2. In other cases, it could be iron +3. Copper could be +1 in certain cases or +2 in other cases. There is 3 exceptions in the transition metal region, which actually do have fixed charges, and that is our zinc and cadmium. Both zinc and cadmium will always make a +2 charge, no matter what the situation is. And then if you hang a left at cadmium to silver, silver will always make a +1 charge. So those 3, zinc and cadmium, always +2, even though they're transition metals. and silver will always be +1, even though it's a transition metal. So they also have fixed charges. Any questions on that there? So that's important to know. Oh boy. All right. So let's talk a little bit about type 1 and type 2 compounds. And when we have just the cation by itself, like I mentioned, we basically just use the whole name. And we have our nonmetal by itself, or our anion by itself, we use the IDE. Always both in formulas and also in the way that we name, we always put the positive guy first. So the cation always comes first, followed by the anion. So it's always cation and anion. This is always type 1 and type 2, always ionic compounds, which contain a metal and a non-metal. And as we talked about, we got our electron transferring over in that case. When we put our formulas together, as we talked about today with bonding, we always want to put the formulas for the ionic compound together in the simplest way that gets us to 0. So earlier we had calcium, right? And we had fluoride. And once again, we want to make the compound or the formula for this. We did need one more fluorine to do so. And that gives us a -2 charge and a +2 charge, which equals 0. And once again, the proper formula would be something that looks like this. That formula, when we put the metal and non-metal together in the formula for the ionic compound, should never ever have a charge. So the CaF2 should never have a charge. But it should be remembered that it actually is representing 3 things that do have charges. It's representing 1 calcium with a +2 charge, which is the cation, and 2 fluorides, each at -1, that have charges. But when we put those charge guys together to write the formula for an ionic compound, always has to equal 0, and the simplest way to do so. The real reason behind that is what we talked about today. The real reason behind that is that it allows, as we saw, everybody to reach the noble gas configuration, right, when they come together. And that's why we got to put them together that way. So that's why when we take something like Na+, which is sodium, and chloride together, that's +1 and -1, which obviously equals 0. So we just need 1 of each. And once again, although that NaCl has no charge, it is made up of 2 things that do have charges. You know, if we had something like Al 3+ and Br-, the proper formula for that should be which one do we need more of to get to 0? More of the positive or negative guy? Yeah, we need a grand total of 3 of them, right? That gives us -3, which balances out the +3 that's there. Now all you have to do is count. I have 1 aluminum. I have 1, 2, 3 bromines. And now I have my correct formula there, AlBr3. So again, when we put them together, it balances it out. Any questions on that? Okay. All right. Let's talk about type 1 and type 2 compounds. Let's super zoom in. Type 1 and type 2, as I mentioned, these are always ionic compounds, so they're always our metals and non-metals together. Whenever you have an ionic compound that's type 1 or type 2, because it always is the metal and non-metal together, whenever those 2 things come together, the most important thing is always this guy. It's always the metal that is the most important thing. Who cares really about the non-metal? It is actually the metal that tells you how you should name these guys and how you should go about naming these guys properly. So what makes something a type 1 compound versus a type 2 compound? A type 1 compound, you look at the metal, and the metal comes from either group 1, 2, or 3, or zinc, cadmium, or silver. What all those guys have in common is if you look on the periodic table and you see the metal in one of those locations, what they all have in common is that they all have fixed positive charge, which means they always have the exact same positive charge, no matter what the situation is. And when you have that situation, you can name it type 1 way. And type 1 way is basically whole name of the metal and IDE for the non-metal. A type 2 compound is where the metal, again, is the important guy, and the metal is a transition metal and are just to the right on the periodic table where we have lead, tin, etc. underneath the staircase. These guys have a variable charge, obviously, except for zinc, cadmium, and silver. And when you see that type of metal involved, you do have to do one additional step when you go to name it. And if you see the other type of metal, you don't have to do that additional step. So it's always important to focus in on the metal when you are dealing with ionic compounds. And it's really the location on the periodic table of the metal that helps you understand sort of how you should go about naming them. All right, so here's some examples of type 2 metals, like chromium could be +2, +3, and as I mentioned earlier, copper could be +1 or +2. So here are some positively charged ions by themselves. Again, you can see just use the whole name. And then in each of these guys, these are our negatively charged guys. They all have that IDE ending to it when we name it. Some take a little bit more of the back part of the name. Some leave a little bit more of the back part of the name. But basically, you drop the back part of the name of the element and replace it with IDE. So let's talk about type 1 and how to go about naming it. When you have a type 1 compound, once you identify the metal is a type 1 metal, you should be happy because there's nothing more to do at that point other than name it. So when you do it, you will take the whole name of the metal. The non-metal, you will drop the last part of the name and add IDE, and that is all she wrote on that game there. So if I took something like NaCl, Na is a metal, sodium, Cl is a non-metal, I would focus my attention on the metal, which is sodium. I find sodium in group 1 on the periodic table, which tells me it is a type 1 compound. It has, as a type 1 metal, it has only one charge, which is +1. And once I do that, all I have to do is roll to my naming here. I'm going to use the whole name of the first guy there, the metal, which would be sodium. Second guy gets the IDE at the end of it, so chlorine becomes chloride in this case. When we do our CaO, for example, Ca is calcium, which is a metal. O is oxygen, which is a non-metal. So by the way, right there tells you this is ionic, right? When you have a metal and a non-metal together. Once again, it is the metal that is the most important here. Calcium is in which group on the periodic table? Is in group 2, which means does it have a fixed charge? It does, so that's all you need. So we're going to go with the whole name here of calcium. Oxygen then gets the IDE part of it. It becomes oxide. Yeah. Any questions on that there? CaBr2 would be what? It would be calcium bromide, IDE. Once again, calcium is a metal, Br is a non-metal. As we just talked about with the one above there, calcium is group number 2, which means it has a fixed charge. I use the whole name for calcium. The second guy gets an IDE. The 2 here does not matter in terms of naming. You should not do any type of prefix because you think it sounds more chemistry-like, yeah. So there is no dibromide happening here. A big X happens if you put dibromide. So Doesn't matter if there's 2 of them. Doesn't matter if there's 6 of them. Doesn't matter, honestly, if there's 2 or 6 of the first one either. It doesn't matter in this type of naming. That is all you do. Whole name of the first guy, IDE on the second guy. Doesn't matter how many of each of those things you have. It's always the way that you name it. Any questions on that there? There's a time and place for prefixes, and this is not the time and place for either of those. So again, here, if we look at this example, Ki, we would look at K, which is potassium, which is a metal. We would look at I, which is iodine, which is a non-metal. We would look at the location of potassium, which is the metal on the periodic table, which is group 1. That then tells us it's a type 1 compound. And that's all we need to write the whole name of the metal. And the non-metal there getting the IDE treatment, and we have potassium iodide. Once again, the formula here has no charge, but it is actually made up of 2 things that do have charges. It is made up of a cation that is K+, and it's made up of an anion that is I-, right? So again, we just need one of each of those to get to 0, and that's why the formula again has no charge. But it's important to remember that actually is representing things that do have charges, but when we make the formula, we don't write the charge in. Any questions on that there? All right, so why don't we try some here? Maybe I'll switch it out here. Let's do I think we did that one. So let's do Mg. Let's do MgI2. Why don't we also write the formula for, let's do lithium sulfide. Let's do aluminum oxide. And let's do calcium phosphide. All right, correct formula here on the right, correct name on the left. Okay, let's take a look. So we'll start on the left here. So again, the best thing to do is identify what you're dealing with. I got K, which is potassium, that's a metal. I got Cl, which is chlorine, which is a non-metal. First off, that tells us it's an ionic compound because that's always the case, metal and non-metal. Also tells us it's, in terms of naming, going to be either type 1 or type 2. We look at the metal, which is the most important thing, and it's potassium, which is group 1. That tells us it's a type 1 compound, and that's fixed. And that's pretty much all we need at this point. So we're going to roll with the whole name of the metal, which would be potassium. And once again, the non-metal will get the IDE treatment at the end and dropping the last part. So it'll be potassium chloride here. This is made up of a cation that is +1, right? K+ is the cation. And the anion would be Cl-, right? Would be our anion in this case. Any questions on that one there? All right, I crossed this one out and we went with the one above it. So once again, magnesium, which is a metal. I, which is iodine, is a non-metal. So once again, that combination tells us it's ionic. Looking always at the metal, we see magnesium is group number 2, which tells us it has a fixed charge. Also, again, tells us that is type 1. And that means we're just going to go with the whole name here of the metal, magnesium. The non-metal gets the IDE ending. Once again, no effect on the name, the 2 there. It has absolutely no effect on the actual name there. Any questions on that one there? This is made up of a cation that is magnesium with a +2. and an anion, which is iodine, that's -1. And that is why we need 2 of them to balance out the charge with the magnesium. So that's why we have 2 of them there to balance out that charge. Looking at here, we got barium, which is a metal. We have hydrogen, which remember is actually a non-metal. So this again is going to be ionic, or named like ionic. It is barium, which is group 2 that has a fixed charge, type 1. So this is going to be barium. And this is actually the negative version of hydrogen because it comes after a metal, and that is hydride. The cation here is barium with a +2 charge. The anion is actually hydrogen with a -1 charge. And again, that is really the only time that hydrogen will be negative, when it comes after a metal. So if it comes after a metal, it is the negative version. And once again here, we need 2 of the hydrides because +2 and -2 now will balance out to equal 0 in this case. Any question on any of the names there? When we're going backwards from sort of formula to our name to formula, we want to identify what's going on. So lithium sulfide, lithium once again is a metal. Sulfide is a sulfur, which is a non-metal. What we really want is we can identify these as being ionic, and we just want to write the basic units of each of those things. So lithium is group 1, which means it should have a +1 charge. Sulfur is group 6, which means it should have a -2 charge. And basically, we once again want to put this together so that we equal 0. And in that particular case, we need more of the positive guy or the negative guy in this case. We need more of the positive guy here, right? So we actually need 1 more. That's going to give us +1, and +1 is +2. Equals by -2 on the other side, that equals 0. And like I said, at this point, you could just count what you drew. So I got 2 lithiums and I got 1 sulfur, right? And there we go. Any questions on that there? You okay? Yeah. Okay. That's good. I'm sorry. Sorry. So next one is aluminum oxide, which is again, aluminum is a metal. Oxygen here is a non-metal. So once again, it's ionic. Aluminum is our fixed charge there at group 3, which means the aluminum should be +3. Oxide, let's put it out there. Oxide is oxygen. The simplest way to get to 0, and one of the easiest ways to do that is just simply multiply the 2 numbers together. 3 is 6. That will get us to 0. So at that point, since I know I got to get to 6, aluminum is +3, so I need to +6. For my oxide, I actually need a grand total of 3 of them, right, to get to -6. Now I could just count up what it says. There's 2 aluminums and 3 oxygens. Yeah, gives us L2O3. Any questions on that there? Lastly, calcium phosphide. Calcium is group 2, so that's going to be a +2. It actually has a -3 charge, and in this case, it's going to be our same sort of combination there. Our common number between those two is going to be 6. So again, once we figure that out, we just need to get everybody to 6. So for our to -6, for our calcium, if it helps you draw it out, we need 3 of them, right, to get us to +6. Now we can just count up what we got going there. That's 3 calciums and 2 phosphorus. Yeah, and that would give us our right formula there. Any questions? Do that there. So sometimes people teach you like this move of crisscross, and you could do that, and it does work like 93% of the time. Does not work 100% of the time. So if you just blindly crisscross, there will be a number of occasions where you will get the wrong formula and all that kind of stuff happening. But if you're good with like 90 some odd % of the time, you can do it blindly and crisscross. If it's, I think it's better to just figure out the charges, balance them out. You'll definitely always get the correct way doing it that way. But just so you know, it's very commonly taught to people like crisscross and all that kind of things. And it does work in a lot of cases, but there is a number of cases where it will not work correctly for you. So keep that in mind if you roll with the crisscross. Yeah. Any questions on type 1, guys, here? All right, then let's talk about type 2 compounds. Type 2 compounds are once again are metal and non-metal. They're once again ionic compounds. And once again, always in the situation where we have the non-metal and metal. Who cares about the non-metal? It is always that metal that is the most important. So in a type 2 guy, like we talked about, the metal will be a transition metal, or just to the right of it, underneath the staircase, where you have things like lead, Pb, Sn, Bi, bismuth. Those guys all have variable charges. So here the metal will be a transition metal, or just to the right. And again, it's going to have that variable positive charge. Now, the good news is we name it pretty much the same way. The only difference is because the metal could have multiple positive type charges depending on the situation, we do have to include an extra thing in our name to tell people what the charge is. We also need to sort of figure out what the charge on the metal is to do that properly. So if we take the one like in their example, FeCl2, we would look at the metal, which is iron. This is our non-metal. So once again, it would tell us it's an ionic compound. When I see the iron, I look at the periodic table. It's like dead center on the periodic table in the transition metal region. That is iron. So as soon as I see transition metal, I know it could have a variable charge. So the first thing I want to do is really figure out what the charge is on it. You can figure out the charge relatively easy because you will 100% of the time know exactly what the charge is of what it is bound to. So in this case, it is bound to chlorine or chloride. And chloride is group 7, which means it has a -1 charge. There's not just one of them there, but there actually are 2 of them there, yes? Which means if I add up my total negative charge, I got a grand total of -2 happening there from my Cls, which means in order to balance out the -2, the iron has to be +2 here to balance it out. And that is how we kind of work our way backwards to figure out the charge. How do we name these guys? We use the whole name of the metal, just like the last one. We use the non-metal that ends with the IDE. The additional thing that we do is in between, we use a Roman numeral. And it's really important that the Roman numeral is not how many metals you have, which is a very common mistake. It is the actual positive charge on the metal. So if you took one of the metals out, what the positive charge would be on the metal, that is the positive charge on the metal. So if we take our example here, we would start with the whole name, which would be iron. We would do Roman numeral 2 because the charge on that iron is 2 as it disappears and comes back in a very awkward way there. Let's try that again. Let's get rid of that name there. All right. So the Roman numeral again is the charge on the metal. The last part is Cl, which is named just like we did type 1. I don't care about the 2 on the Cl. It doesn't matter to me. This is going to be chloride. Once again, no prefix here. Yes, so this is going to be iron, Roman numeral 2 chloride. Any questions on that there? Why do you have to do that? If I had FeCl3, what would the name of this guy be? Yeah, so we would do the same thing. It's basically metal, non-metal. Our iron is a transition metal. So once again here, we would want to figure out the charge on the iron. We have not one, not two, but we actually have three of the chlorides in this case. That gives us a -3, which means to balance out the chlorides in this case, the iron's actually carrying a +3 charge, which means, as you correctly said, the name here would be iron Roman numeral 3, once again for the charge on the metal, and it would still be chloride at the end there. So because the top one is iron 3, we frankly need to tell people, in this case, it's the iron with the +3 charge. In the first case, it's the iron with the +2 charge. Because there's possibility of it being +2 or +3 in the name, you have to literally tell a person, this is the one we're dealing with. We don't need to use the Roman numeral on type 1 compounds because they have fixed charge, which means if it is sodium, it's always +1 no matter what the situation is. It cannot be anything other than +1. So there's no need to use a Roman numeral for that. That is also why when we have any of those three transition metals, the zinc, the cadmium, or the silver, because they have fixed charges, even though they're transition metals, you don't need Roman numerals for those either because they always will be those charges. So anything that has a fixed positive charge like type 1 compounds does not need the Roman numeral because it is always that charge no matter the situation. Anybody that is a type 2 metal does need the Roman numeral because it has the possibility to have different charges, and you have to tell somebody the charge. In neither case, type 1 or type 2, you should never, ever, ever, I'll say it one more time, ever have a prefix rolling with those guys. Yeah. So if you find yourself doing a Roman numeral and a prefix, just put an X on it. Is probably wrong. Yeah. So they should never cross over into a type 1 or type 2 compound. Any questions on that there? There's one chance where it could happen, but it's not in this case. So what would the name of this guy be here? PB, which is lead, O2. What is the proper name for this guy? And then let's take a look. So here PB is a metal and O is a non-metal. So this is definitely an ionic compound. Again, it's going to be the metal that's important location. This is our transition metal region. Lead is actually to the right of it, as we talked about, below the staircase. So although it technically is not a transition metal, it is named the same way because it can have a variable type of charge. So this is really a type 2 compound as well. We will do our same little move here to make sure we don't screw up. I'm not sure what the lead is, but I do know oxygen is group number 6, which means it should have a -2 charge, and there are 2 of them. That gives me a -4 overall charge, which means the lead in this case is actually +4. This would be lead Roman numeral 4 because of the charge, and this would be oxide. Any questions on that one? This is a prime example of if you just blindly flip, you're going to end up with like lead 2 and it's going to be wrong. Yeah. So this is a case where crossing over will not work correctly. And there's a number of other cases where it will not work correctly as well. So keep that in mind. Again, if you blindly cross over, do so with some risk. About 8 to 9% risk, I think. Maybe a little less. Any questions on any of that stuff there?